In this movie, we solve a calculation problem by resolving vectors into their x and y components instead of having to draw a scale diagram. Let's pretend that we have a tree and two men are pulling on this tree. Perhaps they have ropes tied around the tree. One of them pulls to the right and the other one pulls not completely to the left, but somewhat towards us in the picture, out of the picture and to the left. So how will this tree actually move if it does move under the influence of these two men's pull? Well, it's not going to move either to the right or in the direction of this man pulling, but something in between. It's going to accelerate under the influence of the combined force, also called the resultant. So if they pull hard enough, if the roots are not very deep, then they might be able to actually pull this tree down. And where will it fall? It will fall under the influence of the red arrow, the resultant. Now, there aren't actually three forces acting here. Here's one man pulling, and here's the other man pulling. There's no man pulling over here on the resultant. But the resultant is the sum, the vectorial sum of the forces of the two men. It's the single vector which has the combined effect of these two men's forces. So our question is asking us, what is the magnitude and direction of this resultant on the tree? Obviously, we need to be able to have some values to be able to answer what the resultant is. So let's say that the man that's pulling to the right pulls with 50 newtons magnitude of force, and the direction is to the right. And the man pulling sort of out of the picture towards the left, but not exactly to the left, is pulling with a magnitude of 40 newtons. And let's say that the angle between these two forces is 140 degrees. Now, you must try and understand that this picture that I've now got on the screen, it's as if we're looking from the top of the tree. So here's the trunk of the tree. So there we have the branches coming out like that. But of course, we're not going to include the tree. So we're looking from the top now, not from the side. The previous pictures, we were looking from the side. Now we're looking from the top. And from this information here, we can work out what the resultant's magnitude is. We could do this by doing a scale diagram. Maybe we could say that 1 centimeter represents 10 newtons, and then we would draw this 50 newtons as a 5 centimeter long line pointing to the right. And we would draw this one as a 4 centimeter long line. And we'd make sure that we use a protractor to accurately measure that the angle between the two is 140 degrees. How would we find the resultant of these two using a scale diagram? Well, we'd have to move one of the vectors so that the tail of that vector that we moved was on the head of the other vector. We call this the tail head method or the triangle method. Remember, we are allowed to move a vector as long as we don't change its orientation. So this angle to the horizontal would have to remain 140 degrees. Be careful, it's not this angle that would be 140. Otherwise, we would have to have twisted our vector, which is not allowed. So we may move vectors as long as we don't change their orientation. We also may not change their magnitude. So if we use the scale given here, this one, even after moving, should be 4 centimeters long when we draw it. And then what would we do to find the resultant? Well, we would just simply close the triangle. The resultant is always the vector that goes against the flow. You see that here we have tail, head, but the resultant goes the opposite way. Its tail is on the tail of one of the other vectors, and its head is on the head of one of the other vectors. That's how you can tell it's the resultant. It's not one of the other vectors to be added. And then we would simply measure the length of that resultant and convert it according to the scale. And we'd also have to measure the angle. Maybe we would measure that angle there, and we would give that angle to the horizontal. But now, there is another way to do this calculation without having to draw a scale diagram, and that is using resolution of vectors into their components. So let's go back. Here is our question. We have these two vectors acting on the tree. What is the resultant? So we place these vectors on our Cartesian plane. Now, we can place this Cartesian plane wherever we like. back. Yes, it's true, we call this one x, which can be seen as horizontal. And that in this case is not going to be a problem because we're going to use this left and right. So this is going to be to the right of the tree, this is going to be the tree's position, and this to the left. And we will call directions to the right positive and to the left negative. But now, what we call the y-axis or the vertical axis does not actually literally have to be vertical, as in up-down. Remember that we are looking at this tree from the top. Here are the branches of the tree, the fronds, because it's a palm tree, I think. And here's the trunk of the tree, and we're looking from the top. So this axis here is not actually, in this particular case, going to lie up, down, vertically. Instead, it's going to be, we could say, out of the page, towards us in the picture, and into the page, away from us in the picture. And yet we're still going to call it the vertical, the y-axis. It really doesn't matter, because we can place this Cartesian plane wherever is of greatest use to us, and this is going to be of greatest use to us. But instead of referring to out of the page and into the page, we are going to use the direction positive for into the page and negative for out of the page. Then we need to remind ourselves about the trig functions. You might want to pause the slide and refresh your memory quickly. Another thing we need to remind ourselves of is how to find the horizontal and vertical components if we know the angle to the horizontal. Again, you might want to pause the slide and refresh your memory. So what we're going to do now is we're going to take each of those forces that each of the two men is applying, and we are going to find the horizontal component of each and the vertical component of each. And then we're going to add the two horizontal components to get the resultant's horizontal component. And we're going to add the two vertical components to get the resultant's vertical component. And from that, we're going to find out, well, what is the resultant? So let's do that. We start off with the 15 Newton to the right vector. This one's very easy. All of it is acting horizontally. None of it is acting vertically. Vertically, remember, being into or out of the picture in this particular case. And then we're going to take the more difficult vector, 40 newtons at 140 degrees to the 50 Newton force. And there, it's not so easy just to see by eye what its horizontal and vertical components are.